Welcome to Uiua for Absolute Beginners number 5. We are looking at Advent of Code 2018 Day 2. It's an inventory management system. The final code is shown here. I'm going to delete it and we'll build it up bit by bit, but just wanted to show you, the scale of what we're looking at. So here are the answers to part 1 and part 2. So you may have some familiarity with the problem. We'll discuss it very briefly here. So let's get rid of the code. So part 1, we're essentially looking for how many strings. So here's a collection of strings have exactly 2 of a letter or 3 of a letter. So here's our sample, just reading in from a file. So A, B, C, D, E, F doesn't have any repeats. B, A, B, A, B, C has 2 A's and it has 3 B's. So it has a 2-peat and a 3-peat. This one here has a 2-peat. This one has a 3-peat. This one has a 2-peat and another 2-peat. This one has a 2-peat and this one has a 3-peat and another 3-peat. So we need to find, we're given a list of words, we need to find how many of them have a 2-peat, how many of them have a 3-peat, and multiply those two numbers together. All right, so here's my sample down here. And to start with, well, we're going to use classify. So let me just see, what does classify do? Classify, let's say A, B, A, B, A, A. Right, you can see the pattern there. It's like A, B, A, B, A, A. So it just assigns unique numbers for individual elements, and then it reuses those as necessary. So that's and then we can call group on that. Now group requires 2 arguments. That's why we get an error here. Okay, I don't really know why that. Group needs a function. So if I try ID, no. If I try box, there we go. So it's this magic code here. So I want a group and I want the function to be box. So take what you've got and box it up. And I'm comparing the numbers with themselves, basically. So it's put all the zeros together and it's put all the ones together. And then I want to get the length of each of those. So I could say each length, and I'd get 4 and 2. And what I would do is then deduplicate, which has no effect here, but that's just because if I had a few 2-peats and one 4-peat, I don't really care that I've got a few 2-peats. I'm happy just to have the one. Deduplication's not necessary, but I'm just going to throw it in. Okay, so that's like the order of business. So we're going to classify them and then use the classifications to make groups and then analyze those groups for what kind of repeats do we have? Do we have 2-peats, 1-peats, 3-peats, that sort of thing? But this is, of course, we're working on a list or an array of words, and they're boxed. So I'm going to say each. If I say each classify, then I get those numbers. So you can see like the A, B, A, B, A, B is here, and this is A, B, C, D, E, E. So you can see the 2 4s at the end there. Okay, what do I do now? Well, what I want is to do group, and I'm going to ask for the group the length of that. So I just want the length of each thing. Now I get an error because that produces arrays of different lengths. And if I get arrays of different lengths, then I'd want to box them. I'm going to try boxing it here, but I don't think, okay, so that did work. There's a nicer way to achieve it, but let's just push on and see if we can complete it. So now I've got boxes, and now I've got a box, and now I want to I guess just deduplicate Does deduplicate work on a box? Yeah, it does. Okay, so that worked. Now, instead of putting box here, like instead of being explicit about putting a box, what you can do is you can put pack here. So it's just something I learnt while doing this problem. So pack is like a meta instruction saying put things in boxes if necessary. So if an error would be caused because you are trying to combine arrays of incompatible length or shape, then use boxes. So pack does automatic boxing and unboxing. So this is kind of my only experience of it so far, but I think it's a pretty popular modifier. All right, so now, so this one was to determine occurrences of repeated letters. And so A, B, A, C, E would give us, we have a 1-peat, we have like 3 1-peats, and we have a 2-peat, okay? And that's what it would give us. All right, and now what we need to do is count the number of 2s and the number of 3s. And so you can see here there's one item on the stack, right? And I want to count the 2s amongst these, and I also want to count the 3s amongst them. So that means I want to do 2 things with the one value. I want to call 2 functions on the one value. So that's a case for fork. All right. So if let's say I fork length and reverse, then you can see that produces 2 values based on the one input value. So it's got the length there is 7, and the reverse of the original is there. Okay. Now, obviously, what I want is 2 functions. One is to count the number of 2s. So how do I count the number of 2s? Well, actually, before I do a fork, how about I just count the number of 2s here? So I'm going to, I want to ask, is 2 a member? And before I do that, I need to check, so how do I use member? So I go member 2 and then give a list 4, 5, 6, and that gives 0 because for false. And if I put a 2 in here, then it's now true. If I box this up though, can't look for members of number array in box array. So I'm just not allowed to ask this question. Is 2 a member of this? All right. So the box is not transparent in this case. I don't know why, but there's probably a good reason. So what I need to do first is unbox it. And there we go. All right, now obviously box followed by unbox is a bit ridiculous, but I just need to keep in mind that these are boxed, and so the first thing I need to do is unbox them, right? And so I'm going to unbox those, right? And now running that didn't have any effect, but I don't know if I expected it to. No, okay. It's because I need to call, basically I need to call an each on these. All right, so let's have a look. Each unbox, and that fails because of the, now I've got things of different shapes. So let's just say the length. There we go. So I've got a length of all the unbox. The unbox is not necessary here because you can take the length of a box. But let's just say 2 is, so member 2 of the unboxed. And so now I get 0, 1, 1, 0. Okay, so 2 is a member of some and not of others. And if I replace that with 3, then I get a different pattern. All right. And so anyway, I want to know how many of them are 2s, how many of them have a 2 in it. And so that just means I can add these up, right? Because that will count them for me as if I add them up. So if I do a plus reduce, oops, no, that's because I put too many plus signs in. Okay, so each plus reduce that. Okay, all right, I'm just going to get into my actual code here. So I'm going to do a fork of two functions, right? And I'm going to use rows, which is equivalent to each in this case. And I'm going to do a plus reduce of the rows where, and I'm going to do the member to unbox. Okay, and then I'm going to do the same thing with plus reduce of the rows of the member 3 unbox. Okay, so I've now got 3 and 4. So there were 3 3s and there were 4 2s, and so they're on the stack ready to be multiplied, and I'll just multiply that to get the answer 12. And if I change sample to my real data, then that's that. If we want to look at the real data, I'll just drop it on the stack there. Okay, so we've got I think 250 words that are quite long, and there we go. So the answer 5,976. So here we've got a fork, right? The brackets contain a function. These brackets contain another function. The functions are very similar, and just reading right to left, we're asking for each, or each row. Or if I change this to an each, I'm pretty sure it wouldn't change a thing. So each and rows are equivalent when you're dealing with one-dimensional array. And anyway, so for each of the things is to a member of the unboxed version of it, and then you get 1 or 0, and then you add them up with plus reduce, and so you get the number of 2-peats. Here you get the number of 3-peats, and now we multiply them together. Okay, so part 2, we've got data that we need to deal with. So not so easy to see there, but I wonder what's the shape of that data. So it's an array of 250. I might just reshape it into 250 columns and 250 rows, 1 column. Well, there we go. That gives us a better look at it. So that's like a column vector now, and it's boxed. Now, spoiler alert: we need to unbox it. Okay, we need to unbox it, otherwise the performance prevents us from solving this problem in a reasonable time. The reason it's boxed is because it's been read from a file, and it just so happens that all of these strings are the same length, but that's not even guaranteed in the problem, let alone reading from a file in general. So that's why they're boxed. So I will get to the more efficient solution, but I'm just kind of building up to it. And the one where we deal with boxes is definitely messier, but I think there are probably some things we can learn from it. So we will start with our sample data. And what we're really doing here is, and I'll just move these down under the comment. So what we have is, here are some strings, and what we're looking for is the 2 strings that differ by only 1 letter in the position. So A, B, C, D, E is similar to A, X, C, Y, E. Right, the A, C, and E are common in the correct position, but the X and Y are different. So that differs in 2 places. So it's not the one we want to find, but it's close. And here we've got F, G, H, I, J, and here we've got F, G, U, I, J. So the U is different from the H, and that's the only difference. So these are the 2 things we pick, and then our answer would be, what do they have in common? So we have to answer F, G, I, J. Okay, so we've got a sample, and I'm going to do a table. So let's say a table, say X equals 2, 3, 5, 7, and 11, so some prime numbers. I could do a multiplication table of X with itself and get that. Okay, so that looks like you should understand what that is. So here's the function. If I were to change the function to something like couple, right, then it makes pairs out of them. And so now we've got a more confronting shape, 5, 5, 2, right? So, okay, here's your 1, 2, 3, 4, 5, and here's your 5, and here's your 2. So 5 by 2 matrices we have now. So a table is good for making something like a multiplication table, right? Well, I'd like to have a table here of sample with itself. So what kind of table can I make? How about I'll do a join of sample with itself. Okay, so this basically, I want to consider every pair of words, and every pair of words will be considered in a table. Right now, I want to do something other than join them, but maybe I could work by just joining them, and and see how we go. But let's have a look. If I did that, what could I do with each one? So no, see, I can't use each because yeah. No. Okay, all right. I'll get back to how I was intending to solve this. So sample, and then I need a copy of it. And now I'm going to do a table. The table needs a function. Now the things are boxed, so I'm going to call both unbox, because table will put two things on the stack, and I need to unbox both of them. So that oops. Okay, now that's no good, because I've unboxed both, but that produces two values. But table's function signature must be 2.1. Like, it has to consume two things from the stack, and it has to leave one item on the stack. But I'm leaving two items on the stack. So once they're unboxed, how about I join them? There we go. So that makes a string, right? Now, I can't do anything with that, but I'm just slowly building up here. So if I unbox both of them, what could I then do with that? Well, I'd like to say, where are they not equal to each other? Right, so this is like a mask to say where they're not equal. If I change it to just equal, right, then the 1, 1, 1, 1, 1 means they're the same. And the 1, 1, 0, 1, 1, that's exactly what we're looking for. They're equal everywhere except for one place. So I really want to find that, okay? But it's easier computationally to find where they're not equal. Okay, so this is the one I'm looking for. I'm looking for the thing that has only one place where they're not equal. So so let's add them up. All right, and so what we have now is, like, for our 7 by 7 table of words, we have a number that says in how many places are they not the same. So there's one there and there's one there. Now the table's symmetrical because you're considering words A and B is the same as considering words B and A as far as this table, like this function, is concerned. Okay. Now, and I can turn this into a Boolean array by saying does it equal 1? Okay, and so what I can do now is let's keep the sample, right? Okay. I'm actually going to do this slightly the longer way, the way I originally did it. It's not very nice, but it does have some cool things in it. So I'm going to actually, like, where I've unboxed them and then taken the not equal, applied the not equal function, that means that the two strings won't exist anymore. It's being consumed by the not equal function. Well, I'm going to keep a copy of both of them. And now I can't produce, like I'm producing three things, but what I'm going to do is put them in a box. Okay, there we go. So I've got the numbers. Now here's what I want, right? The rest of them are 0. There's 2 ones. I want to find the ones. So I have the places where they're equal, and I have the I have the 2 strings. So I have everything I need to carry on. Now this is let's look at the shape of this. Right, it's 7 by 7 by 3. So 7 groups of 7 by 3 matrices. What I'm going to do is I'm going to reshape it so that it's a bit more, well, one-dimensional, or not exactly one-dimensional, but so this is a trick. I want to, that's a -1, right? The width of this is 3. I basically, instead of 7 by 7, I want it to be 49.3. Let's do it that way. Okay, so I've now got rid of any gaps, and it's now a 49 by 3 matrix. So which means I can now call rows and work on all of these rows, right? And so, like for instance, I could say equals 1. Does the first item in the row equal 1? And that gives me right? That tells me yes or no. So that's just an example. But when I replace this with data, all right, look, if I don't know what the data is, then the 49 can't be correct, or is not necessarily correct, right? So what you can do, and I'm pretty new to all of this, is you can give it a -1, and that will basically it'll say it fixes the width of 3, but this is saying, like, you know, allow it to fill as many rows as necessary to contain all of the data. So I don't have to calculate the size of the shape that I want. I just tell it, yeah. So I like to understand it better, but you know, that's another day. All right. So now that it's like that, I can work it in rows, and I can actually, I'm going to sort this, right? I'm going to select, I'm going to say fall, because I want to sort it in descending order. Dot, so that's just using an idiom for sorting. And now these 2 1s are up the top, right? And so I'm just going to take the first of those. Okay, so now I've got this, and then I'm going to drop the drop 1. So now I've got the actual, like, 2 words. Right? All of this to find the 2 words. Now, there are definitely better ways to do this, but we learn from, like, not so good ways as well. So now that I have, right, okay, so I have the 2 words, right, what do they have in common? So what I'm going to do is I'm going to, if I call unbox, that doesn't do anything. I'm going to call for each unbox, there we go. So I'm digging inside and I'm unboxing each thing. And then, like, I want to do a comparison of these, but they're in an array, they're not on the stack. And there's a couple of ways to get things from an array to the stack. Here's one I like, right? If you have 2 things on the stack, there's your 6 and 17, and you call couple, then it turns the 2 items on the stack into an array. So the opposite of that, well, if you have 6 and 17 as an array there, you can call the inverse of couple. Right? So I haven't really used it in my videos, but inverse is a thing in Uiua where a lot of functions have an inverse, and couple has an inverse where it does the opposite thing. So that's really cool. Right? So I've got these, I've unboxed these things, and then I'm going to inverse couple them. So now they're on the stack, and now that means I can I can do an equals, right? And that gives me 11011, and then I can, if I could just keep one of those things, I can apply that as a select, right? But I got rid of those things. So what I've got to do is say equals. If I go equals dot, then that gives me 11111, right? If I do equals comma instead, it gives me the right thing. So let's just see about that, right? So here's what I've got on the stack. If I do a dot, then you can see the dot duplicates the top of the stack. And so those two things are guaranteed to be equal because that's what dot does. If I do a comma instead, it reaches over that. It's called over. And so now it duplicates a second thing on the stack. So now I can do a proper comparison and I will have something left to use afterwards. So I've got the dot, I call equals, gives me the mask, and then I can use keep to, and there's my answer. Right? And if I change this to data, then you can see here that it's like not giving me an answer. It's too slow. They're doing table operations on a 250 by 250 array is fine, but if the 250 by 250 array has boxes in it and you have to unbox them, then it's not fine. Now, that's just my experience. I can't give a detailed comment on where the performance problem is. Like, you know, who knows? Maybe if I changed this in some subtle way, it would all be good. But anyway, for now, tables and boxes don't seem to mix all that well. So I'm just going to rescue this and put that back. Okay, and so now we're going to try a different approach, right? One that works better and is just a better code anyway, right? But this was the path I took to get there. All right, so we'll start with our sample. And now I'm going to unbox it right away. Unbox for performance, oops. And better code. So my sample, there we go. So I've got to call each unbox. Right. Now, if the problem, like you could make a variant of this problem where the words are not all the same length, right? So then maybe you'd have to use a fill tactic or something like that to make them the same length and keep your performance. Now, I'm going to find pairs of words that differ by only one letter. Okay, so there's a bit of a, like, I was going to say in a normal programming language, that's rude to Uiua. In a lot of other programming languages, you'd look at this and go, oh, that's a one-dimensional array of strings. So if you did a table, now I don't need to unbox anything, so let's say I did table join. Let me just be clear, you don't need to put brackets here, but of course, if I know I'm going to build a more complicated function, then I'm just going to put brackets to start with. Okay, so if I run this, that didn't exactly join any words, did it? Right? And if I get the shape of this, like 7542, I'm now in a 4-dimensional array, and that's not cool. All right, so yeah, I look at this and instinctively think, oh yeah, 1D array of words, cool. I can do a Cartesian product of those. I work on every pair, no worries. Like, so that's one reason why boxing is good. It simplifies things. It says, yeah, I know, see, to Uiua, this is a 1x5 array, a rank 1 array with 5 items in it, right? So the shape that I have here, just to be clear, right, is 7x5, 7 rows, 5 columns. And when you do table, like I didn't really expect this. I thought that table would still work with this because I thought table would just dig into like the surface level of the array, the major axis, I think called. But as we saw, it digs down until it finds the atoms and makes pairs of those. All right, so table is off the table here, pun intended. All right, but I need to get every pair of these words. And there's a generalization of table called combinate. And if you do combinate, what you need to do is provide, I don't want to get the terminology wrong, but provide like a shape that you want to work with, or the rank or something. I'm not good with this vocabulary at the moment, unfortunately. If I do combinate 0, 0 join, then I get the same as before. So, and that's because it's got this from the documentation. Combinate 0, 0 is equivalent to table. Now the zeros here refer to the rank of the data you want to work with. And these things like W and J are each individually rank 0, right? They're scalars. And so if I change this to 1 and 1, what I'm telling the combinate modifier is, or sorry, is it a function? I think function. A combinate function that I'm telling it that I want to work with rank 1 data on both axes. And so there we go. I've now got what I thought table should do, but I was wrong. Well, it now works. That's really cool. So, okay. So now instead of calling join, I can do a different function, and I don't have to unbox anything. So I can really tread the same ground as before now. Okay, that wasn't good. Now table and combinate both need like 2 lists to work on. No, yes, they do. Yeah, I showed you my prime multiplication table before. I said table times xx. So if I just go back to this, right, I'm just going to call this x, right? And so there's my collection of things, right? And I'm just going to put a separator in here just to right. So all right, okay, that's coming from here. All right. Right, excuse me, sorry. Okay, so I've got x, here's x, and if I call table join xx, then I get that great big collection. And if I call combinate 0, 0 xx, then I get I didn't give a function. Right, then I get the same thing, right? And if I do that, then I get like nice one by, get every pair, which is nice. Now, so with this on the stack, right, I need to take at least 1 copy of it. I'm going to take 2, and now I'm going to use combinate here. Combinate 1, 1. Okay, and so I've still got that. That'll be needed later. All right, so instead of join, what are we doing? We're doing not equal. Right, so that gives valuable information, and I'm looking for the ones that have only one of them. So I need to do exactly the same thing before, do a plus reduce, and I need to put this in a bracket because it's a function. Okay, all right, getting somewhere. And then as before, I'm only interested in the ones that equal 1. So we've now got a Boolean mask. Now, here's a cool thing. If you have a string, a Boolean array and you call where on it, then it will tell you the indices where it's non-zero. And until recently, that only worked on one-dimensional arrays, but now it works on multi-dimensional arrays. So if I just keep that, you can see there's a 1 here at index 1, 4, and there's another one at 4, 1, and that's what where has told us here. So that's nice. And what I can do with that, and if you take a good look at back here, this value that we still have, that the 1 and 4 actually corresponds to index 1 there and index 4 there. So I don't actually even need to look this up in a 2x2 table. I can just go back to the original one-dimensional array, right, and just use this 1 and 4 as indices into here, and it will give me the strings that I want. So if I get rid of that, I don't need to keep that lying around. I will take the first of those, so I've got 1 and 4, and then I'll use select to use these indices into that array, and I now have the things that I need, and I of course, now I have the 2 words. I can literally take this. I have the 2 words. What do they have in common? There's no change to this code. Oh yes, there is. So I don't need to unbox anything. All I need to do is uncouple them onto the stack and then call right. So and there's our answer, right? So if I change the sample to data, remember before on the code that I've commented out here, data was not giving an answer in a reasonable time. This is giving the answer instantly. So, pretty cool. We're still doing the data has 250 items in it. So this 250 by 250 table is doing the same calculations as was happening before. The only difference is that we're not unboxing. Right, and in this case, so there's no unboxing apart from at the very beginning, and we're able to use a multi-dimensional where, which was very nice. Okay, so that's it for this video. Hope you enjoyed it.